Hello everyone. Welcome to the lecture on vibration and control method. This is our final video lecture in the unit 5. As you can see on the screen, this unit covers four key areas that are fundamental to understanding and mitigating the unwanted vibrations in mechanical systems. First, we will explore the control of natural frequencies. Second, we will see the introduction of damping. Then the third, we will see vibration isolation methods. At last, we will go for vibration observers. Now, we have an overview on the topics we will be covering in this unit. Let's dive into the first and arguably most fundamental method for controlling the vibrations, manipulating the system natural frequencies. As the title suggests, this slide outlines some important methods we employ to control unwanted vibrations. You will notice that these points directly correspond to the topics just introduced in our previous slide. Here, the first point emphasizes the importance of controlling the natural frequency denoted as omega n and crucially avoiding the resonance. Resonance occurs when the frequency of an external excitation force is closer to the natural frequency of the system. This can lead to a dramatic increase in the amplitude of vibration, potentially causing damage or failure to the systems or structures. Therefore, by carefully designing our systems to have natural frequencies that are far from expected excitation frequencies, we can significantly reduce the risk of excessive vibrations. Then, the second important method is the introduction of damping mechanism. As we briefly see in here, the damping dissipates energy from the vibrating system. By incorporating the damping elements, we can limit the amplitude of vibration, especially when the system is subjected to external forces. And effectively, we can prevent an excessive response even if the excitation frequency is near the natural frequency. Further, the third point focuses on the use of vibration isolators. These are specifically designed to reduce the transmission of excitation forces from one part of the machine or system to another. For instance, if we have a vibrating machine, we can use isolators to prevent these vibrations from being transmitted to the supporting structure or other sensitive equipments nearby. Then at last, the fourth method is adding an auxiliary mass neutralizer or known as vibration observers. This is a clever technique where we attach a secondary mass spring system to a primary vibrating system. When properly tuned, this observer can be effectively counteract vibrations at a specific frequencies, significantly reducing the response of the main system at that particular frequency. So you can see we have several powerful tools at our disposal to control vibrations. In subsequent sections, we will delve deeper into each of these methods, starting with the control of natural frequencies. Now, let's focus specifically on the first method we mentioned, that is control of natural frequencies. As we discussed, the primary motivation behind control of natural frequencies is to avoid phenomenon of resonance. Here, we are clearly representing and illustrating the determinantal consequences of resonance. When a system experiences resonance, it leads to large displacements, which in turn generate large strains and stresses within the material itself. If the stresses exceed the material strength, it can ultimately result in the failure of a system. Think of a bridge swaying excessively in the wind or a machine vibrating violently. These are often examples of near resonance conditions. It is important to recognize that in many practical situations, we often cannot control the excitation frequencies. For example, a machine might be subjected to vibration from its operating environment, or a structure might experience wind loads with varying frequencies. We don't always have the ability to change these external forces. Therefore, we can't always control the excitation frequency. The logical approach is to control the natural frequency of the system itself. Recall that the natural frequency of a single mass spring system is related to the mass and stiffness equation itself. This means we can alter the natural frequency by simply changing the mass or stiffness to avoid the resonance. However, in practice, changing the mass of a system can often be difficult or impractical. Redesigning components significantly alter the mass can be costly, time consuming, and might affect systems' overall performance or functionality. Consequently, a more common and often more feasible approach to controlling the natural frequency is by changing the stiffness of the system. This can be achieved in several ways. We might choose a different material with a higher or lower Young's modulus, which directly affect the stiffness. Alternatively, we can also alter the number and location of bearings or supports in structural systems. Changing the support conditions significantly influences the overall stiffness of the structure and its natural frequencies. So, while both mass and stiffness influence the natural frequencies, altering the stiffness is often the more practical route for engineers to tune a system and to avoid the resonance. We have discussed controlling the natural frequencies to avoid the resonance. Let's move on to our second key method for vibration control, that is introduction of damping. As we acknowledged earlier, in many real world applications, a system might be required to operate over a wide range of speed or be subjected to various excitation frequencies. In such cases, it might not always be possible to completely avoid resonance conditions. This is where the introduction of damping becomes particularly crucial. One way to introduce damping is by carefully selecting the materials used in the system's construction. Certain materials possesses inherently high internal damping characteristics. This means that as the material deforms during vibration, a significant portion of the vibrational energy is dissipated within the material itself as heat, thus reducing the amplitude of oscillations. Interestingly, the way components are joined together can also significantly influence the overall damping of a system. Using bolted or riveted joints as opposed to welded joints can actually increase damping. The reason for this increased damping in bolted or riveted joints lies in the fact that these types of connections permit some degree of slip between the contacting surfaces when subjected to vibration. This microscopic slip generates friction, which effectively dissipates more vibrational energy compared to the rigid connection provided by a welded joint. However, it is important to note while bolted or riveted joints can be beneficial for damping, They also come with certain drawbacks. These joints can sometimes reduce the overall stiffness of the structure compared to a welded connection. Additionally, the relative movement at the interfaces can produce debris due to wear and can also lead to a phenomenon called fretting corrosion, which can weaken the joint over a period of time. Therefore, the decision to use bolted or riveted joints often involves a trade-off between increased damping and potential reductions in stiffness and long-term durability. So, introducing damping is vital strategy for controlling the vibration, especially in situations where avoiding resonance entirely is not feasible. We can achieve this through material selection and even though the design of our structural connection. Building on our discussion about introducing damping, let's now consider some specific way it is achieved in practice. Viscoelastic material. Viscoelastic materials are particularly effective in providing internal damping. These materials exhibit both viscous and elastic characteristics, allowing them to dissipate significant amount of energy during deformation. They are often characterized by a damping loss factor, often denoted by the Greek letter eta, and viscoelastic materials typically have larger values of eta compared to purely elastic materials. This higher loss factor signifies their superior ability to damp out vibrations. However, a significant disadvantage of viscoelastic material is that their mechanical properties, including damping characteristics, are not constant. They can be quite sensitive to changes in temperature, frequency of vibration, and level of strain they experience. This variability needs to be carefully considered during design process to ensure consistent damping performance under different operating conditions. To leverage the excellent damping properties of viscoelastic materials while mitigating some of the drawbacks, a technique called constrained layer damping is often employed. This involves sandwiching a layer of viscoelastic material between two elastic layers, typically made of metal. When this composite structure vibrates, the shear deformation of this viscoelastic layer dissipates energy effectively, while the outer layer provides stiffness and constraint to the viscoelastic material, which in turn enhancing the damping performance. An interesting point to consider is the stress distribution within a damped system. Generally, the material with the largest damping loss factor will be subjected to the smallest stress. This is because highly damping material absorbs more of the vibration energy, thus reducing the stress that would otherwise be transferred to other parts of the system. This principle can be useful in designing systems where certain components need to be protected from high stress levels. So, viscoelastic materials and techniques like constrained layer damping offer effective ways to introduce significant damping into a system. However, it is crucial to be aware of the temperature and frequency dependencies of viscoelastic materials to ensure reliable vibration control across the intended operating ranges. We will continue our exploration of vibration control methods in the next slide. To further illustrate the concept of damping, Here in this slide, I am providing some representative values for the loss coefficient eta for various materials and equivalent viscous damping ratio for different types of construction and arrangements. Looking at the table on the left, you can see the loss factor eta for a range of common materials. Notice the significant differences. For instance, polystyrene has a relatively high loss factor, indicating good inherent damping. Hard rubber also exhibits substantial damping with a loss factor of 1. In contrast, materials like aluminum, iron, and steel have much lower loss factors on the order of 10 to the power of minus 4, signifying that they dissipate much less vibrational energy internally. Materials like fiber mat with a matrix cork fall somewhere in between these extremes. These values highlight the importance of material selection when designing for vibration control, especially when relying on internal damping. Table on the right shift our focus to how the construction or arrangement of components influence the overall damping of a system. Here, damping is expressed as an equivalent viscous damping ratio, often represented as a percentage of critical damping. As we touched upon earlier, welded constructions typically offer relatively low damping with damping ratio in the range of 1 to 4%. In contrast, bolted constructions generally provide higher damping ratio ranging from 3 to 10%. This increase, as we discussed, is primarily due to frictional losses at the bolted interfaces by microscopic slip. A typical steel frame structure might exhibit damping ratio between 5 to 6%. Finally, we see the impact of viscoelastic materials in conjunction with structural elements. An unconstrained viscoelastic layer on a steel concrete girder can provide damping ratio of 4 to 5%. However, when a constrained viscoelastic layer is used, as we discussed earlier, the damping performance is enhanced, resulting in the damping ratio in the range of 5 to 8%. These tables provide a tangible sense of the damping characteristics associated with different materials and construction techniques. When designing systems where vibration control is critical, engineers carefully consider these values to select appropriate materials and joining methods or to incorporate specific damping treatments like viscoelastic layers to achieve the desired level of vibration reduction. Let's move on to our third method for controlling the vibration, that is vibration isolation. Unlike damping, which dissipates vibration energy, vibration isolation aims to prevent or minimize the transmission of vibration from a source to sensitive receiver or the surrounding environment. The fundamental principle of vibration isolation is to insert isolator between the vibrating mass and source. The goal is to reduce the response of the protected system to the forces generated by the vibrating source. Most common types of vibration isolators are passive isolators. This typically utilize elastic materials and structures such as springs, cork, felt, rubber mount, and pneumatic isolators. These materials and design introduce flexibility into the transmission path, which when properly designed can significantly attenuate the transmission of vibration at certain frequencies. A classic example of where vibration isolation is crucial is the mounting of high-speed machinery such as punch press, as shown in this image. These machines generate significant impact forces and vibration during their operations. Without proper isolation, these vibrations could be transferred to the building structure, causing noise and potentially damaging the nearby structure or affecting other sensitive equipment. The next, these images are illustrating some common types of passive vibration isolators. This image shows a spring isolator often used for heavier equipment. Image B shows rubber or elastomeric mount which provides both isolation and some degree of damping. Image C shows another type of elastomeric isolators designed for different load and frequency requirement. These are just a few examples of the diverse range of passive isolators. The effectiveness of a vibration isolator depends largely on the frequencies of the exciter and dynamic characteristics of the isolator itself. We will see in subsequent sessions some of the vibration observers also. An active isolator is a more sophisticated system that incorporates a servo mechanism. This typically includes a sensor to measure vibration, a signal processor to analyze the vibration data, and an actuator to actively generate forces that counteract the incoming vibration. This active control allows for much greater flexibility and effectiveness compared to passive isolators. The effectiveness of any vibration isolator, whether passive or active, is often quantified in terms of transmissibility. Transmissibility is defined as the ratio of amplitude of the force transmitted to the foundation or motion transmitted to the isolated system to the amplitude of the original exciting force. Lower transmissibility value indicates better isolation performance. There are two main types of isolation situations we often encounter. The first is to protect the base of a vibrating machine against the large unbalanced or impulsive forces it generates during operation. In this case, we want to minimize the forces transmitted from the machine to its support structure. The second situation is to protect a sensitive system or instrument from the unwanted motion of its foundation. Here, the goal is to minimize the transmission of vibrations from the base to the isolated system, ensuring its stable and accurate operation. Understanding these two distinct isolation objectives is crucial because the design and selection criteria for the isolator might differ depending on whether we are trying to protect the foundation from the machine or machine from the foundation motion. Active isolators with their ability to adapt and generate counteracting forces often offer superior performance in both of these scenarios, although they are typically more complex and costlier than passive systems. Now, let's delve deeper into the principles behind vibration isolation, focusing on the forces involved in two common scenarios. The first common objective of vibration isolation is to protect the base or foundation of a vibrating machine from experiencing large unbalanced or impulsive forces generated by the machine operation itself. In this diagram here, we are having a vibrating machine of mass m mounted on a rigid base or foundation through an isolator, which is represented by a spring with stiffness K and a damper with C. Then the force transmitted to the rigid base is the force exerted by the isolator itself. This force is composed of two components, spring force and damping force. The goal of effective vibration isolation in this case is to minimize transmitted force to protect the foundation. The second important objective is to protect a delicate instrument or machine from the motion of its foundation itself. The situation is clearly given in the diagram B. Here we have a delicate instrument or mass mounted on a base or package that experiences some external motions. Again, the connection is through an isolator with the stiffness K and damping coefficient C. The absolute motion of the instrument is x of t. Understanding this force relationship is crucial for designing effective vibration isolation systems. Let's focus on the specific case of a vibration isolation system where the vibrating machine is mounted on a rigid foundation using a resilient member. As we discussed in the previous slide, the core idea of vibration isolation is to introduce a resilient member between the vibrating machine and the rigid foundation or base. The resilient member acts as a buffer aiming to reduce transmitter forces from the machine to the foundation. For the purpose of analysis, this resilient member is often modeled as a parallel combination of spring with a dash part. So this is the modeled resilient member. Here in this diagram, the more conceptual representation of machine resilient member and foundation is provided. In both the diagrams, we have a machine with mass M subjected to harmonic force. This represents a common scenario where a machine generates vibration at a particular operating frequency. The resilient member, modeled by the spring and damper C, connects the vibrating machine to the rigid foundation. The spring stores and releases energy while the damper dissipates energy, both playing crucial role in the isolation of system performance. Our goal is designing such a vibration isolation system to minimize the force transmitted through the resilient member to the rigid foundation. Let's turn our attention to the concept of vibration observers. We will start by understanding the problem they aim to solve and then look at the basic principle behind their operations. We discussed earlier a critical issue in vibration, it is resonance. This occurs when the frequency of the external excitation force coincides with the natural frequency. When this happens, the system can experience excessively large amplitude of vibration, which can lead to noise, discomfort, and structural failure. A dynamic vibration observer offers a clever solution to the problem. It is essentially another spring mass system that is specifically designed and attached to the primary vibrating system. The key idea is by adding secondary system, we can effectively change the overall dynamics of the combined systems. So our goal is to shift the natural frequency of the resulting system away from the troublesome exciting frequencies. Let's examine a simplified model of an undamped dynamic vibration observer. Here we have a machine with a mass m1 that is subjected to harmonic excitation force F0 sin omega t. acting downwards. This machine is mounted on a rigid base through two isolators, each having a stiffness K divided by 2. So the total stiffness of the supporting machine is K itself. Now we introduce the dynamic vibration observer. It consists of primarily small mass attached to the primary machine. In this simplified undamped model, we are neglecting any damping elements in the observer. X of t represents vertical displacements of the main machine M1. X2 of t represents the vertical displacement of the observer of the mass M2 relative to the main mass 1. The key to the dynamic vibration observer's effectiveness lies in carefully tuning its parameters, specifically the mass and stiffness. The observer's designed such that its natural frequency is equal to the excitation frequency omega that we want to suppress in the system. When the excitation frequency omega coincides with the tuned natural frequency, the observer mass will oscillate relatively with very large amplitude. Importantly, the force exerted by the observer spring K2 on the main mass M1 will be out of phase with the external excitation force. This out of phase force significantly counteracts the excitation, resulting in a significant reduction in the amplitude of vibration of the main machine at the specific frequencies. Building upon our understanding of the undamped observer, let's now consider a more realistic scenario, damped dynamic vibration observer. As we briefly mentioned, incorporating damping into the observer design significantly improve its performance and addresses some of the limitations as well. As stated here, the amplitude of vibration of the main machine can be effectively reduced by adding a damped vibration observer, as illustrated in this diagram. You will notice that this diagram is very similar to the previous one, but with crucial addition is there. Within dynamic vibration observer enclosed in the dashed rectangle, we still have the mass observer, that is mass M2, attached to the main machine M1 via a spring with stiffness K2. However, we now also have a damper with a damping coefficient connected in parallel with the spring K2. The damper C2 plays a critical role. It dissipates energy within the observer system. This energy dissipation helps to limit amplitude of vibration of the observer mass to especially at resonance. Further, the presence of damping broadens the frequency range over which the observer effectively it can able to reduce the vibration of the mass M. With the introduction of damping, the reduction in the main mass vibration amplitude is no longer theoretically zero at a single tuned frequency, but is significantly reduced over a range of frequencies around the tunnel frequency. This damping helps to control the response of both the main mass and the observer mass, preventing excessively large oscillation of the observers. The optimal value of the damping coefficient C2 is compromised. Too little damping and the observer's amplitude might become large and effectiveness might still be narrow. Too much damping and the observers might become too stiffly connected to the main mass, reducing its ability to oscillate out of phase and counteract with the primary vibration itself. Again, x1 of t represent motion of the main machine. X2 of t represent the motion of the observer mass relative to the main mass. In summary, The inclusion of damping in a dynamic vibration observer makes it more practical and robust solution for controlling unwanted vibrations. It provides effective vibration reduction over a wider frequency band and keeps the observer motion within reasonable limits. Design of damped vibration observer involves carefully selecting the observer mass M2 and stiffness K2 as well as damping coefficient to achieve the desired level of vibration reduction for the main system under its operating conditions. We explored key methods for vibration control, including manipulating natural frequencies to avoid resonance, introducing damping to dissipate energy, employing vibration isolation to block transmission, and utilizing vibration observers to counteract specific frequencies. We discussed the principal and practical consideration for each of these techniques, including the benefit and drawbacks of different approaches like material selection, joint types, viscoelectric materials, and tuned mass dampers. Here, I am concluding this Unit 5. We have covered lot of ground from the fundamental principles of avoiding resonance, introducing damping to the practical application of vibration isolation and absorbers. Hope this unit has provided you with a solid understanding of the tools and techniques available for managing unwanted vibrations in engineering systems. Thank you again for your engagement throughout this unit. Thank you for your attention.